record. All right. Sorry, last study set. And nuclear is great. You just think of this as your equal sign, periodic table we get to use. So we want to fill in the lower numbers from the periodic table. So iron is 26. Again, this number, we're not going to use the masses here. So you're going to be given the mass number. And the mass numbers are never going to be on the periodic table because these are unstable isotopes. And so they're going to be the really rare ones. So you just go with whatever it is. So a neutron gets a 0 down below because the lower number is the number of protons. So just a reminder, that is the symbol for a neutron. So 1 over 0 and little n. So the particles are always lowercase letters. And then the arrow you consider as the equal sign. So the top and the bottom just have to equal. So 26 plus 2, this is going to be 28. And then this is going to have a total of 58. So we'll subtract 2 from that. So this is number 56. And so element 28 is nickel. All right, aluminum is 13 and 2. So we have 15 total. So we will have a 0 down here and a 1. So it's a neutron. And again, you can write like that, or you can write the word neutron. All right, molybdenum is 42. Deuterium is, so hydrogen, remember everything. Can you guys see it okay? I guess you just have to see the final answer. I can lower it. I did really small font. Every element has multiple isotopes. So whatever mass number I give you, you just go with it. They're not going to make sense because this is unstable nuclei. So what the periodic table is showing you are the stable ones. All right, we have a lot of neutrons here. So we're going to have 98. So it's going to be 97 total. So 1 plus the 97 gives us 96 plus 2. And then our lower is going to be 42 plus 1, which is 43. So we look up and we find it's TC, technetium. So technetium on this periodic table is yellow because it's actually man-made. It's a man-made element, and it should be a lowercase c. So capital T, lowercase c. It was made, I'm pretty sure, at Hanford. That's the one I was telling you the story. One of my students' grandfather. We have technetium again, different mass number. That was the other thing I wanted to mention is when you look at a lot of periodic tables, oh, it's on this one, you'll see some of these with parentheses and they give you whole numbers. That's because they only made one isotope. So that's what those whole numbers mean. And it's so unstable, there's no way they're going to get a mass of it. All right, neutron. I did so many with neutrons. Molybdenum is number 42. So again, atomic number below. And then the mass numbers will be given to you. And we need 99. So this is going to be a 0 on the top because my top part equaled 99. And the lower number needs to be a -1. And so you can here say a beta particle. This is not beta decay. Why is this not beta decay? Even though that is a beta particle.
Because it got larger?
Beta decay, it always gets larger.
Oh, just kidding. I mixed those up.
Because the neutron becomes a proton, right? It is because in decay, there's only one thing falling apart. So these are all actually man-made. These are all man-made processes. And that's, if you see 2 reactants, they're man-made. The exception is our last one here, which, so kind of back to what Damon was just saying, this, like you get really good at this, which you would hope your teacher can do, it's not beta decay because beta decay, they always get bigger. And this one's getting smaller, but it is a +1. So the 8 plus 1 gives us 9. And we show it similar particle, but this is a positron. And again, you will see some places will show it as a 1, as an E. So it is the same mass, opposite charge. So they both have a mass, a really itty bitty mass, but it is important on some scale that they have a mass, because they're not pure energy. These guys are the smallest particles we know of, positrons and electrons, or that I know of. There's so much changing. There's a lot of cool stuff going on. All right, there's something like 9 states of matter now. So somebody like wants to look into that for the innovation paper and talk about it. So solid, liquid, gas is all we talk about, and that's really something that's happened in the past couple of years that they've really expanded. So plasma is just one of them, but they've really expanded the idea of these other states. All right, these are going to be decays because there's only one reactant. So when you have two reactants, it is artificial transmutation, meaning they had to have a collider of some sort to collide them together. So you can, from the periodic table, tell what it is. So because the silver is moving up to the cadmium, so you do want to make sure, though, it will end up being a beta decay. So this is beta. Krypton is 36 and beta would be 0, -1. So krypton's going to move up to the next one, so 37. Mass does not change. All right, Pa is down here. You can tell from how massive it is, it must be down pretty heavy. And so that's proactium, because when it goes through alpha decay, it becomes actinide. Which is number 89. So alpha decay, you always drop 2 down. All right, thorium is number 90, and then alpha we show as a 4-2. You can just write it like that, or you can show the particle. So it's going to decrease a lot, 226 on top and 88 down below. So probably the big, and then 88 is radium, so Ra. The biggest mistake that happens on these is when you're asked to write the equation, and we'll see that on number 3. The alpha, beta, the decay, so these are all natural decay. They are always products. So alpha, beta, gamma are products. And there's only one reactant. All right, bromine is number 35. And again, that number doesn't make sense to 82 because bromine wants to be down closer to 80. So it has too many neutrons. So it's going to go through a beta decay to go to krypton. All right, so you have one like this on your worksheet, but several people did it already. You can show all the individual steps. That's a lot of work. My other class, they always do that. You can also just add up. You have 1, 2, 3, 4 alpha decays. So you can just say, I'm going to lose 4 alpha and then 2 betas. And then what are you left with? So our mass is going to change only by the alpha. So 219. And then we're going to go down by 6. So the alphas are going to go down by 8, but then we add 2 back. So number 86 is radon, which is a gas, which makes it dangerous because we inhale gases. So something I didn't talk about, I usually have 2 lectures on nuclear, and I didn't realize that until I was halfway through. I was like, oh, wow, I usually have 2 lectures on this. They have caves. This area, there's a lot of radium in the rocks all over the world. So those big floods, Kobe can tell me what the name of the floods are from like whatever a million or billion years ago. A lot of rock got pushed to the other side of the Willamette. So if you live over in Beaverton area, there's a lot of radium in the rocks. And so a lot of the houses, their basements actually have a lot of radium in the rock. And radium goes through natural decay and alpha decay and becomes radon. And so they have radon in their basements from that's just giving off there. Our air, if you live out here, I live by the college, we have really low levels. I don't have a basement. My mom lives in New Jersey. They have really high levels. And so her house is from the 70s. We'd moved in there. She's like still one of the original owners. And if she sells the house, everyone who sold the house, they have to pay several $1,000s, and they have to come in and they put in this thing to vent the radon, and it's really expensive. And all it is a PVC pipe. And so it just creates a vent. And I'm like, well, that's stupid. All you have to do is open the windows and it leaves. But you can go to Home Depot and buy a little thing. It's like a little petri dish, it looks like. And so if you have a basement, like I don't have a basement in my house, and you put it in there for, it's anywhere from 1 to 4 days, and it will trap it, and then you send it off, and they tell you if you have safe levels or not. But if you sleep in the basement, just keep a window open would be the motto. Joey was more afraid of other things in the basement back when we had to sleep in the basement once. But anyway, so there's here in Idaho, there's really high levels there's caves. And people go there for therapy. They're called the Radon Caves. I don't know if anybody's heard of them. And so you go in these caves, and people like swear by this, that they sit there and they're breathing in the radon for like 2-3 hours, and they say their arthritis goes away, their inflammation goes away. My theory, I mean, right, the placebo effect, right? But it is, when you're in a cave, what is your cell phone reception like in a cave? You have no cell phone reception. These people have to sit there and just talk to other people. And imagine that, right? You can't look at your Facebook, you can't look at people's opinions about everything, you can't watch the news, you can't hear about what's going on, and you just find bliss. So that's kind of like what my life is like. And so that's probably, I would never go into a radon cave to believe that. But if you believe it's going to make you feel better, it does. All right, so the periodic table, mine's old, like 10 or 20 years, right? These are all now have full names and stuff. So a lot of you probably printed new periodic tables, and this whole row is complete. And so some of them, before they get an official name, they are given like these UU names. So 287, which depending on your periodic table was what was element 114. And so it was made, so this is going to be the product, that they took calcium 48, so calcium's number 20, and plutonium. So I think I mentioned it, but it's worth mentioning again, that the planets are on here in the order. So if you don't know your planets, after Saturn, there's Uranus, Neptune, and Pluto. So they are on there because it does reflect the planets in that order. But plutonium ended up being named after the god of the underworld, and plutonium is a dangerous one because it can go through fission. So plutonium is number 94. So that gives us 114. And then on top, when we add it up, we're missing a mass of 3. So that would be 3 neutrons. When you have multiple neutrons, you have to put the 3 in front. This has to still be a 1 because each neutron has a mass of 1. And the 0 is either the charge or that it's no protons would be the official reason. All right, so this is how it's written out as a sentence. Yeah. All right, any questions from that first page? Okay, let's move on. So gold to become mercury, you could write these out, or you can look on the periodic table. If it moves up, if it gets heavier, it's going to be beta. Like here, you can see it lost a mass of 4, so that must be alpha. Here, you want to always check, so it does, it moves up 1, so this would be beta. You can also go through writing your equations like we did here, so just writing your equation and getting it to balance. And then indium to cadmium is the opposite way, so it's getting smaller. So on your final celebration next week, so this is a positive, oops, you should say beta with the 0, 1. This is a positron. So it'd be a 0. I show the plus just to make sure. You know, always like on your worksheet, you're going to write them out. That's part of it, is that you're showing me, you know, how to write them. But that would be a way to just being able to look at them. All right. The band of stability is on your periodic table. So cobalt 61. So cobalt, we can see, should be closer to like 59. So 61 means there's too many neutrons compared to the stable. So compared to periodic table, to say PT. So that is beta decay. Beta decay, again, is a neutron turning into a proton plus a beta particle. So protons and neutrons are not elementary particles. They think an electron is. That's only because we haven't been able to find something smaller than it. And again, it's possible they have. So neutrons and protons are made up of subatomic particles, and that includes positrons and electrons. And that's where I said, if somebody wants to do something like that as their talk, if you want to talk about leptons, I know that's not like a current event thing because leptons been around, but if you want to like embrace the different types of leptons and give a talk on that, that would definitely be a fun topic. And it's never too late. There is a point it gets too late to change your topic, but you can change your topic. You can just email me or talk to me when we get done. All right, Californium, as I said, these are man-made. So Californium is CF number 98. And Californium 251. So this is not enough neutrons. So it would be below the band. So we're going to do the opposite, which is a proton becoming a neutron. And more, this is, I went through this pretty fast in the notes, but this is what it would be, which is positron. And again, positron is not called decay. I don't know why, but it's called, so my Uncle George is a nuclear chemist. He got his degree in his PhD in the 50s. And so he worked on PET scans, which is positive. So some of you may have had a PET scan. PET scans probably superior to all the others. It stands for positron emission topography. So it's how they can take a very refined scan of our bodies. And that's what he spent his career working on different isotopes to do that. And I could ask him, you know, why is it called emission? And he would probably tell me because that's what it's called. All right, so carbon 11, of course, carbon 12 is what we would want. So again, not enough. So I have to go back and look at this one. I just realized. So this one's the positron. For the Californium, you could either say positron, or these are predictions, or if you had said alpha, because it's just too big. I had mentioned that once you get down here to these guys, they're just all too big. So alpha decay is probably the most common. These again are predictions. You're never going to know until you they do look at the decay and they can capture the different types of particles. So for the Californium, you could have said positron or alpha decay. For the carbon 12, that would be positron, and cobalt is beta decay. That's the bonus is like that on your quiz, your worksheet today. So easy bonus, easy worksheet. So So just do your worksheet tonight and get it in. So that's one thing out of the way. All right, so hydrogen. Every element has isotopes. Hydrogen is the only one in which they named them. So every hydrogen has one proton. There is 3 forms of hydrogen that I am aware of. And it's the only one in which they named them. So the one that everybody knows is protium, and it's obviously called that because it's just a proton. There's no neutrons. 99.9% of hydrogen is protium. The H2 is what they make heavy water from. So that's, somebody one year did heavy water as their topic. That's a really, no pun intended, but it's an extremely dense topic, but it's deuterium, so H2. You just go with it. H2 is actually stable. It is not radioactive. So that ratio actually can work. It's not common. H3 is tritium, and it's probably why that site where the first nuclear bomb was dropped is called the Trinity site. I don't actually know why it's called the Trinity site now that I think about it. It has to do with, there's so much with threes in nature. So, but tritium is radioactive. There's too many neutrons in that. So here, we're going to do cadmium 114. Cadmium is number 48. And deuterium. And so we end up with protium, which is H1. So reminder, this is how we're going to write it, but when you see it as a dash, that is the mass number there. And if we add up, it's still going to be cadmium, but the mass number is going to be different. It's now going to be 115. All right. Yeah. From the periodic table, neither form of cadmium is going to be very stable because they're both going to be too heavy for cadmium's protons. And again, there is the island. It's not the band of stability. There's a whole thing called the island of stability, which is really fascinating. So our nucleus is not a disordered chaos of stuff thrown together, kind of like my room is. It is actually very organized, how electrons have that organization. Okay, so calcium and deuterium. And so again, these are man-made processes. So we need to get to 21 here. So we're going to get a 2 down here. And on top, we need to get to 42. So you could either say helium or you could say alpha. Either one is fine. It's not a helium atom, but it is the same as the nucleus of helium. All right, so that's what deuterium is. All right, fission is, so fission means splitting the atom with a neutron. So you will always see, like here, when it says undergoes fission, you have to add the neutron there. So like that one is. So these first two are fission reactions. And again, there's something like 300, I don't remember the number, ways that uranium can be split. And so you will always be told what your products are. The two products will add up. So whenever it's bromine, you'll get the La57, but the mass numbers will be different. So you always get some neutrons left over. So the one goes in, it splits it, and you always get more out. 2, 3, 4, 5. So we have to add up to 236. So when you add these, you're missing 3 neutrons. All right. And again, not many things can be split like this. There's very, very few. This is the only form of uranium that can go through fission. The only other one I know is plutonium. And we can make really pure plutonium is, all right, so tin One of the tins is actually a really stable tin, not that one. We'll get 3 neutrons. It doesn't matter the order you write them in. It does to some of you, but it doesn't as long as there's a plus sign. And we're missing 42 down below. So 50 plus 42 will get us to 92. So element 42 was molybdenum. And then we're at 134 here. So 131 plus the 3. Over here we have 236. So you can grab your handy dandy calculator. And we're missing 102 total there. So our answer would be the molybdenum 102. So the key with fission is that there will be a neutron here. A lot of people, including your teacher at one point, fission is not a natural process on Earth, except that they have found evidence of natural fission. So they claim in caves in Africa somewhere from ancient times. That brings up a whole other possibility too, but whether that's real or not, I don't know enough about it. All right, tritium is H3/1 plus something, and we're going to get helium or an alpha particle and a neutron. So these last two are fusion. So we just have to add up. So it's looking like it's deuterium. So tritium plus deuterium. So this is what is happening in the sun. Fusion is happening in all the stars. That is the brightness we see. This is, yeah, right. So lithium is number 3, and we end up, oops, arrow, with 2 alpha particles and a neutron. So our total needs to be 8, 9. So we're missing a 2 on top and a 1. So again, deuterium. Deuterium showed up a lot on this page. Oh, I know what I was going to say. So there is also something, didn't mention the other day, but this is kind of cool. So the smaller elements, and this has to do with the next question we're going to have. When we look at the mass deficits, when you add up the parts of the protons and neutrons, it will never equal the mass of the whole. At iron 56, it swaps. So here, when we add up, so when we do this math here with calcium, calcium has 20 protons, so calcium 40 would have 20 neutrons. Question that Omar had asked me, these numbers for proton and neutron, we're just going to use that. You have a question on your lab. So the lab for this weekend is all math. It's a good review for the final. So there's no kitchen chemistry stuff. So you have one of these on there. It's not on the worksheet. There's no math really on the worksheet. So when you add up these, the 20 protons and 20 neutrons, you'll get like 40 point something. Keep all the sig figs. For those of you who love sig figs, you got to keep all of them. And then the mass of the isotope will be given to you very precisely, that the difference between them will always give you a mass deficit. Here, when you're dealing with something smaller than iron 56, the parts are always heavier than the whole. Once you get past iron 56, it flips the other way, that the whole is always heavier than the parts that added up. And so that, anyway, that's kind of cool. If anybody in here knows astronomy, this is like one of the few things I know about astronomy. And it was a student taught me this the first year I was teaching, that all stars, actually, they are going through process to become iron 56. And so that's why stars eventually, like our star will become like a red something. And so the red is from the glow of the iron. And so it becomes this massive thing, which is the reactions in there are happening. So the hydrogen, there is a sequence how fusion happens to make, and you get past the iron, and then these are going to go through breaking down, and everything eventually wants to be. Iron is the lowest potential energy. I don't fully know why. There's probably a lovely reason. All right, on number 9 with the binding energy, again, you just do your protons and neutrons, add them up and subtract the whole. And so we need the change in mass. And then your next step is you're going to take this change in mass and you're going to multiply it by the speed of light squared. But we do need to be in kilograms. So 1,000 grams, we'll divide by 1,000. You do need to be in kilograms. And then this is the speed of light, 2.998 times 10 to the 8th meters per second. That does have to be squared because it's c squared. So, and I like to go to kilojoules. So a joule, just a reminder, this is a joule, is a kilogram meter squared per second squared. When you take physics, that will get ingrained in you at some point. We'll change 1,000 joules, 1 kilojoule, or 10 to the 3rd. And then I wanted per nucleon, so we would just, you would just divide by that there were 40 nucleons. So again, a nucleon, protons plus neutrons. And that's where I got my number. 4 sig figs because the speed of light limited us. But that's the idea. You have one like that also on your lab this weekend. So just show your really just 2 steps kind of. All right. Iodine 131 is something that is used to treat thyroid cancer. So it goes through beta decay. So the idea is that the beta particles will target the fast replicating cells. And so iodine 131 will become xenon 131. Mass will not change, it's just the atomic number changes. So the only thing that can change the mass is going to be the alpha decay. So the other ones don't change the mass. All right, and again, a reminder in the decay, the beta and alpha particle are on the product side. All right, so for doing this, if you are given the half-life, this is again, we did these with kinetics. Our first step is natural log of 1/2 equals negative KT 1/2. So state your formula, and we would plug our half-life in, right? It's natural log of 1/2 divided by the negative 0.804 days. Keep it in days. That's going to equal K, whatever K is. And then your second step is that you would just do natural log of AT over AO equals negative K times time. So we would plug our K in here. Our time is the 22.2 days. The A0 is the 3.14159. So Comet, sorry. Thank you. I'm sure several people said bless you and you're all muted, or you thought it at least. I know you all well enough by now. On the lab, there's one of these, and the units are really weird. Whatever the units are, just keep them those units. So these are normal micrograms. You know what a microgram is. The units, they just have to be the same. So whatever AO is, that's what AT is. So it is actually, I think disintegrations per second or curies or something like that. And so radioactivity, there's all these different unique units they use them in. So then you're going to solve for AT. So reminder to get rid of the natural log, you'll do e to the power of negative KT and then multiply by the A0. Our answer, I will be asking you, and we'll see this on the review. so this is the study set's also good for the review, is why the answer makes sense. So it makes sense because I did write your celebration. We'll talk about that in 5 minutes. There's a number of these. So half-life is 8 days, 22 days, so almost 3 half-lives. So not quite, but almost. And so, you know, you're starting at about roughly 3 micrograms. So you'll cut it in half. So it makes sense. After 3 half-lives, we should be around 0.4 something. So that does make sense. We didn't quite make it to 3 half-lives. So you're just doing like a rough estimate when you're saying if it makes sense. Number 11 is the same idea. We have to do natural log of 1/2 equals negative KT. There's that. We solve for K. And then you're going to do your ratio. And the ratio is that 12%. Equals negative KT. So you will do this time natural log, and you can either do the 12% over 100, or you can just change it to 0.123456789. You're going to miss my numbers next year. When you're in other classes, the numbers are always just like 25. Anyway, divided by negative K, that will give you the time. So again, you could approximate 100%. First half-life is 50, 25%. And so this is roughly 3 half-lives to get to 12.5%. So the answer makes sense. 6,000 times 3 is around 17,000 years. Yeah, and you should clean your closet. Mine is not. It's accumulated mess. Any questions? All right. Stop. Last homework.